the researchers, students, and PhD students from Chem. And last year we have opened this event to all the PhD students and the master students. And we are happy that step by step this event gain recognition, and we have now many researchers interested to attend it. So this event was created first time for as a result of a project for excellence financing, that PFE, you know, this project like PFE, and it was dedicated to the young researchers. The format is with 1 to invited lectures from gave by well-known personalities in the field of chemistry, and then the researchers, the young researchers, will present their recent results in their activity related to the research, development, and innovation. So we are proud to have several partners like Romanian Society for Chemistry. Here is represented by Professor Andrei Sârbu. And also we have Annelies Plus as a partner and information. Let's start, and also a professor and Dr. Florin Oancea, our scientific director. He is the president of organizing committee of this event. So I want to invite first Professor Sârbu to say something and to invite you to attend.
Thank you very much. I am very happy to be again here in the 5th edition of our workshop. I think that our initial initiative was developed very well during this period. And we started with presentation of master and PhD student from our institute. Now we receive also our PhD student and master from universities, research institutes. And I think that it is a school for these young people to learn how to make a presentation, how to answer to different scientific questions, to have a scientific discussion about their results. So Romanian Chemical Society is very happy to support this organization, because it's one of our main objectives to attract young people to the science, and in our case to the chemistry. So I want to tell to all the participants welcome, and to have a very good presentation, and to acquire new knowledge from this event. Thank you very much.
Thank you very much. And now I want to ask our scientific director to open
Thank you very much. Thank you very much. The idea was to establish a bridge over times, because were famous in Romania in last century, the micro symposia from Chem, which were known as a place where the researchers are formed, are trained. In order to deal with this hard and beautiful job of the researcher, I wish welcome and success to the present meeting. Thank you very much in these difficult and busy times. Thank you.
Thank you very much. Now I want to invite the chairman of this event to introduce the first lecture. Thank you.
Thank you very much. This fifth edition we are hosting today and tomorrow of the exploratory workshop NeXT represents for us a very good opportunity to promote the young colleagues and to introduce them in the hard but very beautiful life of research. We have over 40 participants from national and international institutions. And we also have 3 invited guests, which I want to thank very much for their participation today. Our first invited lecture is presented by Professor Liviu Popa-Simil, Executive Director of Los Alamos Academy of Sciences, USA. Liviu Popa-Simil is currently president of LAVM LLC, a private company developing nanonuclear materials and terahertz applications, as well as security systems, and the executive director of Los Alamos Academy of Sciences, which strives to serve the public good by promoting science and innovation. Nuclear engineer and researcher, Dr. Popa-Simil has built a reputation for excellence over the course of a decades-long career. After graduating from nuclear engineering faculty in Bucharest, Romania, specialized in fast breeder reactors, physics and engineering, and with a dissertation work in laser plasma jet nuclear materials enrichments, he has a broad engineering and computing background. In an accomplished listee, Dr. Popa-Simil celebrates many years' experience in his professional network and has been noted for achievements, leadership qualities, and the credential and success he has accrued in his field. His research interests are covering cutting-edge technologies in industry as robotics, materials characterization using nuclear methods, interferential holography, sound and vibration-based measurements, automotive and navigation electronics, and others, and took part in the study of various singular and abnormal phenomena. He rapidly advanced through his field, serving as an engineer physicist, project coordinator, and senior researchers for IFIN-HH, Accelerator Nuclear Physics Application Division, where he developed nuclear methods and applications in industry and environment, and initiated novel nuclear fuel research and pulsed power applications. He then served as technical director of electron trading, where he was involved in modernizing process control and automation in the processing industry. A pioneer in the study of the secrets of subatomic particles, he devised a method to value the massively emitted energy, a method that, according to specialists, will change the world. Popa-Simil, together with another Romanian, Claudiu Muntele, professor of physics at the A&M University in Alabama, managed to invent a special material made of carbon nanotubes, these materials being used as a protective shield for nuclear power plants. So, Professor Popa-Simil, thank you very much for accepting our invitation. You have the floor.
Thank you for invitation, and thank you for allowing me to give you a presentation here. How does it work? Okay, so I had a little bit trouble to make the presentation because I'm not really a chemist, and I'm looking into nuclear materials and nanoparticles. But in the recent time, I have to deal with some interesting nanoparticle behavior in the form of functional nanoparticles or nanoengine called SARS-CoV-2 and other viruses. So what I like to introduce is in filtration technology on real cases, on starting from the last pandemic on COVID and going into nuclear field in nuclear pollution, in nuclear accidents and possible other bad incidents that we need to develop protections and know how to deal in such situation. So trying to make this short, I'll apologize, I didn't decide what slides to cut and leave, so I will not comment on political alternate realities issues, but even you'll see them on the slides, I'll squeeze them quickly. So let's start. The first problem is to define what are the particles of interest and what is the issue. We'll talk about aerosol particulates and powders in recent work in nanoparticle technology and is a recent pandemic control. First, what are airborne particulates, and we'll make a chart about dimension, magnitude, and see they are defined by having the falling speed smaller than the wind, basically applying Stokes force. In the particle size, this is a laser. What did I give it? This is okay. In the particle size, you have various different particles from the COVID, that is 100 nanometers, to dust particles, to blood cell, just to have a flavor. On the right chart is about, in the lower part, is the falling speed, Stokes falling speed. And every time the wind is higher than the Stokes falling speed, plus a little bit adhesion repulsion coefficient, particle may become airborne. In this situation, the density makes a difference, but you see it's not too much. The time for falling 1 meter is for particles under 10 microns very large. Also, the viscosity of air makes a contribution, but it varies with the air humidity in the temperature domain, and we have various manifestations. How they are obtained? In various civil and military events and weather catastrophes or high winds, they are obtained all the kind of nanoparticles that are airborne, and we make the distinction of these particles in long-range transportation. Basically, most of particles under few microns. In medium-range transportation that have a range about 100 kilometers, and short-range transportation, big particles like dust in urban. In 90s, we measured the elemental concentration of various airborne pollutants, and we made that study in cooperation with Nagoya, Japan, and UC Davis, each of them developing different air quality measurement protocols. UC Davis, Professor Tom Cahill, developed what's called the IMPROVE protocol. But in our experiment, we tried to make a mixture of all of that because IMPROVE was based on laryngopharyngeal cavity arrestance, while Nagoya was mainly oriented for industrial pollutants detection and polluters localization. So we tried mixtures. It was not very successful because we had a lot of incidents and to mitigate, and also appeared a lot of crap. But main results are listed in the Nagoya protocol. Take samples in various positions in town, And we have specific curves. Los Angeles, you see, it's a very polluted place, but has a different specific element distribution, less lead and arsen, while Bucharest has plenty of elements, medium and heavy. And I think was the second place after Los Angeles. But Budapest, Munich were different because cleaner. And that measurements were made using PIXI method, that means particle-induced X-ray radiation emission, where after colliding a helium or a proton beam into the filter that you see on the map, is we can say what is elemental composition and was specific lines measured. In reality, what we need, so we had local sampling, 1 hour, and a measurement, 20 elements 3 times on the particle magnitude. What is the value of such a measurement? Well, it's almost nothing because it's enough to scare, but not enough to help understand and solve the problem. So network for measurement and characterization of pollution in a place requires a lot of resources, about 100 drones, many measurement simultaneous points in order to compensate for weather and airflow, fluid flows, and takes the local pollution in account. So that is not yet achievable. We talked at IEA about this, but no funds. And we'll go as we can. And natural disasters are the main source of aerosol pollution, and also man-made disasters, wars around the world, biolaboratories, and other managed. Bio-nanoparticles, we took in account is viruses, bacteria, and bioweapons. From the point of view of influenza, in the United States, we had influenza that is during Obama time that produced sick people hospitalized with the brown in the top of the cone, and the death with the yellow that is not so visible. And when COVID appeared, it was a kind of shock and awe because it has lower infection rate by higher hospitalization and deaths in a percent. And we had various evolution in our US medical system due to various political trends. Obama tried to improve a little bit, but Trump decentralized, cut funds, and had some other incidents, and we had a high deterioration. This is a study ongoing, both in military and non-military laboratories. It's about understanding the genome equation. As you know, if you look at humans, you may look at biochemical robots made by a long range of programming included in DNA, and that become a functional unit able to take materials from environment and construct and reproduce a structure. And this allows to determine what are the genomic differences and the common structure in order to construct various medicine or other devices. From the point of view of COVID, we had is a difficult entity, can be considered is something like a bioweapon, but also is a class of virus. And it has incubation depending on dose and type of brand of COVID, and also has a stealth infection and seamless propagation. And then symptoms appear, sick, and some goes on ICU, some on ventilator, and so on. Each stage is determined by the internal programming inside the virus and the way it interacts with the body and the immune system. The beauty of big nanomachines of COVID is that when attacked, they can split like a cluster bomb into smaller entities that some are functional, some not, but comes under Darwin influence. And by interaction with the immune systems, they may give other functional devices that will produce wonders of the future medicine. These are various patented spreading methods for bioweaponry or devices. I'll not stay on that. The story tells that in Wuhan, in a live market, the COVID appears. The alternate realities or conspiracy theories suggested two passes, one in United States by Chinese and Russians, one in China by Americans. We didn't observe which one is true, and in the next 100 years, we may not have this information. And these are laboratory searches for various types of viruses spread in the world. And this is the same stuff. These are the propagation stories. The official version of WHO is that it was an intermediate host that is undefined, and from that it propagated in the world in a very strange manner. These are some Vietnamese trying to explain the presence in various places of various brands of viruses, but under the viruses there are the aerosol particulates that also make a contribution to the health of the human. And the impact of human body with nanoparticles, with these functional nanoparticles, is very strange, because from the medical point of view, under the threshold of detection of an illness, the persons feel healthy, but from the person point of view of functional state function, it feels tired, annoyed, have all the kind of not functioning well symptoms without getting a clear diagnostic. Well, in nuclear accidents, we have also radioactive fallout as in S7 incidents, events or accidents, because INES is a scale similar to Richter, developed by IAEA, International Atomic Agency. And we had recently two incidents. One is Fukushima in 2011, and the other is Chernobyl, that produced a high suspension of radioactive and non-radioactive nanoparticles. From the other point of view, we have the development of a large arsenal of nuclear weaponry. And if these are used, they will give also a large combination of nanoparticles in the incidents and large contribution of actinides that from chemical point of view are difficult to separate and eliminate in protection systems. Well, this is mainly the subject. That was the introduction. The subject is how to use technology to make protective system for human life, and to use filters as classical ones. As you may see in the lower side, we have surface filters and volume filters. A surface filter is a membrane with calibrated holes, but has a very steep arrestance curve calibrated as the dimension of interest, while the volume filters have a large capability of stopping particulate but the arrestance curve is not so steep. And we also have another elements for filtration and separation, like ultracentrifuge, electrostatic, cyclone filters, laser plasma selective ionization and separation, Scruber methods, ion exchange, and molecular sieves. Each of that has specific conditions, require specific technology and mainly energy. These are various types of filters for fluids and air. We make an emphasis of HEPA filters used for air purification and the various systems. These are results from 80s when we used membrane filters to characterize lubricant, engine lubricant concentration in particles and using thin layer activation method to label various parts on inside an engine for measuring how much particles they have been removed during operation by the engine in a certain amount of time, and use a stock filter unit in order to have measurement related to particle magnitude, trying to correlate the particle magnitude of where particles that was removed from the surface with material type, annealing, and thermal treatment. And in the upper corner is equipment that we used with radioactive powders obtained by filtration and separation with nuclear reactor activation in order to measure how is the arrestance curve. In the right side curve, you may see the arrestance curve in green-yellow for a surface filter, and the orange is for a volume filter. And that is the main difference. The surface is more stiff. Here is another method of measurement for various labeling or radioactive product separation, like tritium labeling, C14, 32 phosphorus, and use double photomultiplier coincidence equipment and the nuclear equipment. Now, coming back to COVID, it was still a very hot debate about wearing, and for some uneducated populations that turned out to be a political statement, a matter of belief or not belief. It goes into alternative realities. In fact, using a surface filter is that will reduce pollution of exhalation from a few cubic meters to few liters. And that is what you mainly see here. From the filtration point of view, these are arrestance curves from the tables. We'll talk how real they are and how you can use for various kind of filters, high HEPA filters, depending on size from the 300 nanometers to 10 microns. And you will see various samples, like viruses of various shape, that have different behavior on each type of filter depending on many parameters. This is, for example, how N100 filter system at electronic microscope looks for a COVID particle of 100 nanometer. And it was a trend developed to use salty filters to impregnate this filter with in a salty solution or iodine solution. And the belief here was that these viruses are traveling in bubblets And when they reach salt, they dissolve the salt and get active chlorine hydrogen water that attacks spikes. And when the salt is drying, it recrystallizes and encapsulates the virus in bigger particles that can be further stopped in the filtering mesh. These are microscope images of various bacteria, antibacterial nanofiber filters made of various materials. The idea is to use adhesion forces between surfaces of the fiber versus virus in order to produce arrested impact. And here are some watery bubbles and particles trapped into the filters. These filters have a different behavior depending on water presence or without, and they appear phenomena of micro or nanofluidics inside, and that makes big difference in how they behave. For example, we took here 2 samples. In the lower part of the lower part of this figure, we have 2 samples of particle magnitude distribution for an actinide with red curve produced from a nuclear accident, and particle magnitude with violet for SARS-CoV-2 with various distribution of air watery bubbles. And these are MERV versus HEPA and MPR ratings. Basically, when you look at this rating in catalogs, you need to understand the advertisement effect. And depending on what application you are trying to use for, and it's better to know more about how they behave, how they are made. In our previous experiments in Haiti, we studied the filters, various materials, and we, after a few hundred of measurements, we have the following conclusions about that. And this can be generalized to any volume filter. And the upper left side, you see the filter retention factor. The red curve there is released particles that are that pass through the filter, and the R filter is a retaining factor of the arrestance. And that, for example, is put at 0.3 microns, where the arrow comes, and then it goes mildly to smaller particles. So at about 1 micron, our filter retains almost everything, and at 10 nanometers, it retains almost nothing. And the oscillation in the curve is given by various nanofluidics effect instabilities that takes place inside the fiber when the airflow, loaded airflow pass through. Another effect is the variation of the arrestance curve with flow or with pressure that is applied on the filter. And that may change the arrestance. If you put more flow, it will allow bigger particles to pass through. In other variation is the temperature behavior. That is a little bit trickier because it also modifies the arrestance curve and doesn't have the same selection, but that mainly depends on the material that the membrane is made and how it changes the surface adhesion forces or repellent forces. If it's hydrophilic, hydrophobic, with the temperature, these properties are changing, and that makes changes into the filter behavior. Another effect is pulse of bidirectional flow, because you may imagine that a forest or a jungle into a hurricane that retains something, release something, and is a continuous equilibrium between the flow, the particulates, and the parameters. And in our case, we have an accumulation on the filter for a low flow. We increase the flow rate passing through the unit of surface, and we got a spike. The red spike was written drop that makes particles be released from the previous load. Another effect we can consider is the behavior of the filter with clogging or with accumulation of particle on the surface. And in one side, it will move the arrestance curve towards smaller particles, that the filter will become better. But as a drawback is that at any fluctuation or a flow shock, a pressure shock, it will release some of the particle it previously retained. So basically it will be a trade-off between that. Now a mask filter is a combination of several materials. It's not a simple fabric we can add, because the first fabric in contact with skin have to be friendly and not produce any irritation. Then the next will have to behave as a filter and stop and absorb as much as possible. And the last one have to be hydrophobic in order to deal with rain and humidity. Now, in 1920s, after pandemic eruption, we had a lot of guys trying to measure and characterize various type of filter materials in order to produce something, because import from China lagged, and we do not have enough protection equipment in the United States. These are various measurements, homemade test equipment made by universities in the United States, and they characterize the effectiveness of various materials. In fact, what people didn't understand when they were never told was where is the threat, how to protect against, and how to use it in a polite manner. So the reality is that you need to use the mask in the same way you use a beam at a car. In replacing, by analogy, the beam range with a speed range. So when you are coming closer to a person, you raise a shield, put the mask, and the pollution with personal aerosols is limited. While when you are alone, you can use no mask because there's no purpose into that. Mask leakage was an important factor because people look for a very good mask with high retention factor, and that makes pressure drop on the filter be big, and they were lured to make it leak in order to breathe through. So the best deal is to use that protection factor where you can breathe through. And this is how this danger from this aerosolized particle appeared is similar to what you see with the smokers. And here are images of the leak made with laser image in upper left picture. And this is invisible thread you may pass through hallways when somebody released them in air and the air didn't move too much. These are some recommendation appeared in the United States that are more confusing than explaining the population the reality. And from here appeared a lot of debates. Basically, counterproductive, and we have a high contribution to casualties. These are images made by Florida Atlantic University using laser for leakage in the mask, for releases, and to characterize how the various face mask behaves. Basically, what you have to consider is also the airflow in a building and how it accumulates. And depending on how the wind is going, is varying the probability of collision with contaminated air plume. This is how a room may look like after sitting inside for a time. It's known that a man takes about 10 liters per minute of air, while a woman requires 5 to 8 liters. If it sits there for 24 hours, a quarter of or a half of air in the room is affected. Each person makes the atmosphere in his room. So diving into that atmosphere, if it's contaminated, requires individual protective measures. This is transmission in magazines and by breathing contaminated air and exposure by passing and breathing inside the plume. And these are the airborne and close contact and formate transmission. This is what we really need to stop, and without too much pain and panic, and not make a statement out of that. I'll have a comment. Transmissions through skin is not as effective as transmissions through inhalation, because skin is designed by nature as a protective shield. As also you have protective equipment made by nose and buccopharyngeal cavity. So this is about minus 20 decibels protective factor here. Here are various incidents where the airflow is difficult to prevent and needs specific air control technology to stay safe. And in a case of contamination with this kind of virus or newer, better viruses, in few breathing, the infection is transmitted. Well, engineered pandemic control is something mankind knows for 100 years, from Middle Ages plague to modern First World War. And it was basically ignored during this pandemic. But here is way simple to measure. In fact, any filter is enrichment or depletion instrument, and you have to consider for a filter effectiveness the depletion or enrichment factor. That is something that goes up to 10 to the 9 to 10 to minus 9, difficult to handle. The easy way to apply is when in the both sides is the same pressure. You may have not a huge variation in the particles A to particles B, like in our case, red particles versus blue particles. So you may consider a simplified version in decibels, like any directed energy protective device for electromagnetic pulses, for example. And that unit in decibels is easier to handle and to understand. And in different conditions, a mask N99 may give minus 20 decibels in protection, N95 goes minus 13, and the simple diffusion by expansion of the contaminated plume in air by distance gives also a good protection factor. So all ALARA principle can be used in order to obtain the protection you need. This is what happens in a hospital where a physician dives in the atmosphere of a sick person, and he requires a very high protection factor, about 100 decibels, in order to stay protective. But no filter can produce that protection. No individual equipment except PPE, personal protection equipment for full body with autonomous air. That means a bottle of compressed air that is not at all friendly to wear. This is what how looks the distribution of the particles when normally breathing is a red curve that has a maximum about 600 nanometers, while coughing and having accelerated exhalation gives to larger particle magnitudes up to 10 nanometer. The HCl is contamination level, and that means how many nanobodies, aggressive nanobodies, one can emit and attach into a droplet. And this depends of how sick it is, and the lower you have the time in airborne inside the room. And that varies, decreases with the particle magnitude. But what you observe is that almost all the breathing, all the aerosol released by breathing remained airborne. And that flow like a ghost, and depends of air currents you can meet with them. This is also true for those who handle nanopowders. And in the nanopowder, you have to be very careful, because if you move it fast, do some air turbulence near, you get that airborne. And if it's in air, it's hard to stop and put out. And this is what the masks are doing when a leak leaks. It basically damages the protection by a factor of 10. And one effect I will like to highlight is the double filtration. When somebody exhales something through a mask, say N95 was the ultimate mask according to United States NIH. When you exhale that, another person wearing the same mask will inhale almost everything, because what was filtered once is not so much filtered twice. And you might experience with the coffee maker. And that is the effect of double mask from transmission from person to another happens, and the effectiveness of the second mask is reduced, because the particle magnitude already corresponds with the particle magnitudes that are not retained by the mask. There are ways of technologic protection using the air diffusion and releasing the breathe low and inhaling up, and also using the room, releasing the exhaled gas into drain with the sterilizer unit, and also using the AC system with UV and chemical filtration. Chemistry against these functional nanoparticles can play an important role if the right effects are identified, because you can use salty filters. It does something. But if you want to be more aggressive, you need to be careful to the replacement effect of an aggressor with another aggressor. As you use, for example, a cyanide filter, you have to be aware that the particle released by the cyanide will go into breathing system, and now you don't know which is worse. Well, these are various as physical means of protection by using a simple face shield or only nose mouth shield, and very simple objects made by no cause that produce good protection factor by deflecting the exhalation jet. But these are not nice to wear because after a while, all that was placed in air will leak from the deflector and will not look nice. This is how in high contamination, if say bioweapon at level 4 or 5, you will have to encounter and work with increased protection system, both from the building and from individual in a 3-layer of defense. And now a little talk about vaccine pandemic control, because it was a huge debate. Based on New York State medical data, this is what happened. The truth is, and when you breathe something like nano powders, is no way not to have them inside. So while you breathe in, you have them in. How you deal with that depends on the immune system, and the immune system is acting and decide if you get sick or not. From the guys infected, when I mean infected, there is with symptoms, because the guys with no symptoms are not counted. So 2 in 31 I am with symptoms, about 2 in 30 are going to hospital, and 1 in 6 from the hospitalized is dying. So basically, the vaccine protection gives you maximum 32 decibels, while mask and building protection system may drive to 200 decibels, with the difference is first layers engineered protection makes you not to infect. The vaccine is a secondary protection that acts only after the accident happened. So it adds to the first protection. And these are various types of protection based on individual protection to infrastructure protection that drives down to more than minus decibels compared to vaccines that adds another maximum 30 decibels. Wearing the mask correctly, and when it means wearing the mask, is a social effect, because the most important for a mask is exhalation jet reduction, not the individual protection. But due to the selfishness of populations, the individual protection become more important than the collective protection. And not wearing correctly drive to pandemic multiplication and having rates over 1. Complex mass system terminates all viruses, and that was seen in the United States in COVID, because SARS-CoV-1, it's a much smaller animal, it's about 20 to 30 nanometer, and survival rate is smaller and becomes a neutral device. This is engineering solutions that relies on filters, aerodynamics, photonics, and a little bit more. We had some patents, and in order to produce an individual protection system, you need to wear a complex technology and have power. You need to add, if you want to eliminate carbon dioxide from exhalation, you need to add about 15 grams of calcium hydroxide for each minute of breathing, and so on. So it's energy and material intensive, and it's not something easy to wear on the head. And this is the air refurbishing system that is high-tech and is in competition with PPEA that gives lower weight and a simple method. These are schematic diagrams for using this air refurbishing restoring protection that tries to be expensive and elaborate and needs a lot of knowledge, technology, and suffering. Okay, these are filtration systems and the various ways of total protection systems we may encounter in the future exposure. I will pass through very quickly because it's not too much time. So aerodynamics and filtration technology, the chemistry of membrane interaction with the nanobodies is very important to be in harmony with the type of nanobody and regime of use. Here is another effect we can use in that previously protection system that implies a double airflow, one down to take the exhalation, one up, and is based on a Virga effect and aerospike jet devices. This is a hot curtain obtained with aerospike. In the rocket technology, you know there are two types of jet. One is a cylindrical jet that requires a rocket to have 3 stages because it doesn't match the shape of the nozzle with the pressure it operates in from 1 atmosphere to vacuum. And an aerospike that is a rectangular nozzle that allows adjustment. So this kind of nozzle can be used for this type of application, embedded it into tables and chairs and seating with a lot of air control technology. And this is how it works. You put a fan with AC above, with some water droplets evaporate. They make a flow down by cooling the air during evaporation and collect a part of the breathing. So they are sanitized and warm up and go back, making an hot air curtain. But it's sensitive to wind and it may be also doubled with a UVC curtain, UVC having about 253 nanometers as a frequency. So UV starts at 400 nanometers, goes to UVA, and then to UVB from 350 to 280 UVC, and then is UVV, vacuum UV, that goes to less than 100 nanometer. The problem with UV is that the energy of photon is bigger than 3 electron volt, and that is able to break molecular bonds when collide with absorbers like a nanoparticle or molecule. And these are various types of, this will skip them because we don't have time to talk. An important part to consider is for any kind of nanoparticle pollution is inside the speed, the concentrations, the distribution. In our case, we took an example with an exhalation. The values are coming from some measurement that during an exhalation, a person emits about 10,000 water droplets per cubic centimeter. And these are floating in air, and while diffusing into air, it dilutes and travels versus air currents. These are meeting rooms with increased aerosol safety, where the air is made to take all the breathing pollutants and place into harsh vacuum system, where they will encounter sterilization filter that's chemical based, and the UV system. Another big spreader is a toilet and any water jet with vortexes that release also air particulates and need a specific procedure to deal with. High vacuum system sensibilities are an issue to be analyzed, and also you have a measure you can do with using the measurement devices for taking the specific curves of biorhythm at each person in order further to use computer to determine the abatement from the personal biorhythmic characteristic as temperature, heart rate, oxygen rate, and pressures versus the state of the person, and therefore to determine if some infestation occurred. ALARA is applied fully to nanoparticles as is applied to nuclear technology, and that can make a big difference in this. Vaccination individual immunity is in full debate. Basically, we know for many years that it's not effective to make a vaccination campaign during a pandemic campaign because vaccines will be by 3 to 6 months obsolete than the virus, and will take some effect, but not fully. Personally, I have 5 vaccines and 2 COVIDs. And that makes it. So this is how in time various COVID brands varies, and how you are behind COVID with analysis and vaccine preparation. Basically, a system behaves like in this simplified case, the distance between a police car and a thief car. When some bank robbers pass by, they see police and accelerate. Police start that immune system and try to catch them. And the distance between them on time is giving something similar with disease evolution. So if the immune system is active, will take a fast recovery to a relative long recovery. But if the immune system is not aware, doesn't accelerate as well to damage the enemy, the sickness is progressing and the distance is increasing. For playing games, I use that equations just to show how that behaves as an analogy. It's not completely true, so don't take it as I say it, just check it. So from my point of view, after each COVID and each vaccination, my immune system gets mad, and I started to have a kind of arthritis. All the accidents and ligaments in the past I encountered start to be painful, so I need to take some medicine to calm down the immune system in order to be functional and in good spirit. So this is UV effect. UV, I told you, is energy in photon over 2-3 electron volts that breaks molecular bonds and makes active chemical radicals that are easy to interact with other particles in air. And this is physiologic immune system enhancing based on various alimentary supplements. It's a full jungle, so take them with care because they have collateral damage, never knows about, and you learn after that. And this is another application using cell phone GPS tracking that makes post diagnosis calculation of probability of infestation. So calculating the distance between cell phones and correlating with atmospheric winds or air currents you can measure the time, distance, and probability of one person to be infested by proximity to a already confirmed contagious person. And you may put the next question, where that cell phone is, locate and immobilize in location to prevent become a second spreader. That is what China does successfully, and what the United States doesn't do successfully for good causes. We do that for special cases, but in our vision is a privacy infringement, ignoring that the first condition of the cell phone to serve you is to know who you are and where you are. And by courtesy, it tells you the GPS coordinates. And this is how infection rates goes, like a chain reaction. And again, air currents, probability of infestation of release of gases at various altitudes. This is about ISO protocols, clean room versus breathing in a room. And you may see that in ISO 1, if you have one person breathing, it pushes it immediately in a cubic meter in a ISO 9. So persons and behavior in clean room are very important to have the room cleaned and not produce more particles by our activities inside. There are various technologies to deal with that, from individual aerosol collections to the collective and building capabilities to deal with that. A national response to pandemic and hierarchy of controls, take you briefly through it, is like controlling a reactor criticality. And you have a control board, you see in the lower part of the figure, and you have an adjustment curve where you multiply all the levels of control reactivity that are mainly quasi-independent, and obtain the results in making the reaction subcritical. What I mean is, from an infected person in a period of multiplication to transmit to another person is reactivity 1 or criticality 1. When one person transmits to more person, it's supercritical and the pandemic starts. So you need to have it subcritical, a person not to be able to transmit to the next one. And this is kind of administrative personal protection type of measures in all the domains that you have to play with in order to eliminate the pandemic and terminate the rate. Well, that was not the case in the United States. Everybody made that a political issue, trying to gain political points, and for various reasons, they lied, misinform, disinform, or make partial true statement. The reason for vaccine was big pharma gains. Sorry. There was a gain in big pharma that has a good lobby, and that makes that United States with 4% of population to deliver 25% of casualties. Oh, I'm out of time. Okay, I will try to stop here because that will enter into a specific problem. So the fundamental of all this is based on IQ, education, and stuff like that. And let me show the final. So here you have the IQ countries in order. So so that diagonal represents IQ rank from first countries in the world that have 100 IQ to the last countries that have about 50 IQ value average. And we draw the following conclusion. With high IQ, very high IQ drive to low low pandemic, low infection rate. With medium and high IQ, we had not so well behavior because we had good GDP, but also we have a high infection rate, and the vaccination number and the test number basically didn't produce a significant or the expected change in the infection level. Here is a case of Austria, United States, Great Britain, stuff like that. United States is yellow, and China is that dashed red, and in the class B of IQ, there are countries in Europe and Asia. So based on death rate, you'll see that low IQ countries are poor and they have low medicine, and the death rate was higher. And the COVID case is also lower. They have more parameters than simple IQ. And we tried an amplification on education based on PISA tests of various nations, where we see a degradation in education. And Murphy's paradox is IQ, total planetary IQ is constant, while the population is continuing growing. So the key will be education and rising IQ of various population. This is the inflation, and that is based on other issues I do not talk about. I try to stop here. I will not go on actinides and nuclear deterrence. Thank you for patience, and thank you so much.
Thank you very much, Professor Simil. In my conclusion is that with a better education leads a better life for individuals and both the society. This is my conclusion from your final slide, and it is, in my opinion, very true. Also, I think it was a very educative presentation on a very sensitive subject. I do hope that we will never see in the following years, at least, such a pandemic on a large scale. So if we have any questions from the room. If not, I thank you once again, and we'll keep the discussions for the break, because as I've said, this is a very sensitive subject. Thank you. Our next guest also comes from the physics domain. Professor Paul Vassos is a senior researcher at the Extreme Light Infrastructure, ELINP, from the Institute of Nuclear Physics, Horia Bay. He is also an invited professor at the University of Bucharest, a professor of chemistry, Biomedical College, Paris Descartes University. He was also a fellow of the Swiss National Fund, senior scientist at École Polytechnique Fédérale de Lausanne, postdoctoral associate at the Swiss Federal Institute of Technology in Lausanne and the University of Maryland. His main research areas are biomolecular structure and interactions, water biomolecule hydrogen exchange observed using long-lived nuclear magnetization and hyperpolarization, discovery of singlet triplet nuclear magnetic transitions, biomolecular effects of high-dose radiation driven by high-power lasers, observation of the effect of overexpression of cellular transporters on the in-cell transport of endogenous molecules hyperpolarized, coordination of the assembly tests and application of the first dissolution DNP systems, new methods for conserving DNP stemming polarization. He was granted 3 patents filed both in EU and in the US. receiver of the Romania Academy Prize Nicolae Tesla, December 2019. And with a very impressive research impact according all the databases. Professor Vasos, you have the floor.
Thank you very much. It is an honor to be here. Thank you for the kind invitation and for the kind introduction. It's a place where I used to come a lot when I was very, very young. So it's really a pleasure to be here. And I want to talk about timescales in spectroscopy and how we can adapt the timescales that we observe to the phenomena that may occur fast or slowly. And we do this using symmetry, namely magnetic symmetry. And I'll explain what this is about. And the particular application I would like to address is a new type of treatment for various types of cancer, of solid cancer, consisting of delivering radiation in very short times. It's named flash radiotherapy. And I want to show what spectroscopy can do in this context, what the biomarkers proposed by spectroscopists can do in order to predict the response of tumors in terms of flash radiotherapy efficiency and toxicity. And what are these biomarkers based on? So we are all familiar with interactions on different time scales. And one thing is that such interactions occur mainly from a symmetry break. If you separate positive and negative charges, this will lead to electrons orbiting around the nucleus. It's a type of interaction. It has a time scale. It occurred from an original symmetry break. And in Plato's book, it's stated that even human interactions occur from an initial symmetry break, that initially we are all androgynes, and the jealous gods, in order to diminish our strength, as they were envious, they sent a thunder, and this broke us in two different types of humans, male and female, and that since then we have been interacting as well. So the idea is that changes in symmetry lead to interactions, to systems trying to recover their original state. And a very interesting aspect that we should keep in mind is there are degrees in these breaks of symmetry, and the higher the symmetry damage, the longer the time scale for the recovery is going to be. And there is a phenomenon that we are all familiar with. It's called phosphorescence, and this corresponds to seeing light from a system even after we switch off the triggering light. And this, you all know, is due to the magnetic moments of electrons being forced to change symmetry as they pass from the higher energy state to the lower energy state. When the electrons do not change their magnetic their magnetic symmetry, when couples of electrons do not change their magnetic symmetry, when the system is recovering, then this transition occurs much faster, and it corresponds to what we know as fluorescence. So a change in the magnetic symmetry from the one state to another can seriously alter the timescale on which we observe a transition. And we use this in order to study the phenomena, because after all, when we observe timescales in various phenomena, we use other phenomena as clocks that are attached to whatever is going on. So we have a little observable phenomena that's a little wristwatch, and this is our observable, and the molecules that we observe undergo the biological process that we want to monitor. And there are various examples of such biomarker molecules. There are biomarkers that can be observed in the UV visible domain, and they are usually, they have these cyclic structures, they are fluorophores, but their main issue is that they are a bit bulky, and as soon as we attach them to a biological molecule of interest, it changes significantly its structure. This is something we do not want to do. We do not want to attach a bulky lead to a molecule that we want to observe. We would prefer to be a little bit less invasive. And also we would prefer to see in depth in the organism where light does not necessarily enter. And a way of doing this is using magnetic resonance. Magnetic resonance looks at the magnetic transitions of nuclei inside molecules such as glucose. And these are magnets that are naturally present within molecules, such as hydrogens have magnetic moments, carbons, some of the carbons, carbon-14 isotopes have magnetic moments, nitrogens have magnetic moments, nitrogen-14, nitrogen-15. So these are spies that occur naturally within the molecules that we want to observe and that we can see within the body and without perturbing the molecular structure. And another type of marker we all heard about is radioactive nuclei that we can attach to molecules in a non-invasive manner, but their signal is radioactive, such as fluorine 18 in the detection modality known as positron emission tomography combined with computed tomography, so PET-CT. I come from High Power Laser Institute you heard about, and I want to tell you the relevance of a high power laser in observing biomarkers in the context of radiotherapy. High power in this LINP laser does not mean a lot of energy. It just means a short time scale. So really moderate amounts of energy, tens of joule, are delivered or up to 200 joule, are delivered to a target in a very, very, very short time. So the time scale is on the order of femtoseconds. And this is what gives the time, the high power. And if you convert this in radiobiology terms, this corresponds to flashes of energy or to flashes of dose. So this corresponds to delivery of high dose rates. And of course, if you deliver a lot of energy to a system in a short time, then you can expect all kinds of effects. You can expect to create organic matter from simple molecules, such as in the Miller-Urey experiment, or you can expect to break organic matter, and this is what happens in radiotherapy. And I'd like to explain a little bit this new idea in radiotherapy of delivering radiation on very short time scale. It also incidentally comes from two groups from the institutes where I have worked in the past. One is Centre Hospitalier Universitaire de Lausanne, CHUV, and the other one is Paris 5, where I was a professor before I came back to Romania. So this flash radiotherapy was developed in the last years by the group of Marie-Christine Vosnon in Lausanne and Vincent Fauvaudon in Paris. And the reasoning behind it is that if you deliver a lot of radiation in a short time to tissue, then the toxicity effects will be less, and this will stay local. The toxicity will not spread. So as you deliver, as you create oxidation effect, if you will, in a reduced region of a tissue by delivering all the energy there, in a short time scale, when the spread of toxicity will be less. And they have started doing these studies on in a preclinical context, of course, on mice. And what they saw was first at the physiological level, where the mice were observed behaviorally to have improved memory. They are treated with flash radiation compared to standard radiation. And they were also observed to develop less damage of a level of brain related to inflammation that could be observed by X-rays, structural investigations within 2 to 6 months after the application of radiotherapy. And then the domain extended to now it's in the stage of clinical trials. The first patient has been treated a couple of years ago at the Lausanne hospital with flash radiotherapy for a skin tumor. And this was satisfactory in terms of toxicity. There was a patient who was relying on standard radiotherapy, and there was inflammation and redness at the therapy site over and over, and it apparently flash delivery did a little bit better. And we have to understand why there is a difference in delivering a lot of radiation in a short time scale and delivering it on a time scale of half an hour, minutes, as we do usually. Flash proposes to deliver this type of radiation on a time scale shorter than milliseconds. So it's fractionated delivery. That's pulses of can be of tens of microseconds, but within a maximal duration of several milliseconds, you deliver tens of gray. So where could be the sources of differences? One source of a difference is that in order to have effects of radiation, you need fuel, and the fuel is oxygen. So if you consumed all the oxygen in a flash, when you apply the radiation, the oxygen has no longer time to diffuse back to the tumor site, at surrounding sites. So you no longer create further free radicals, so you reduce toxicity. You just consumed all the oxygen you had available locally. So it's a problem. One kinetic phenomena that could manifest in here is the diffusion of oxygen. But there are multiple timescales that could intervene in these systems. It's the kinetic timescales of superoxide dismutase, of catalase, of whatever deals with the free radicals created by radiation. There are natural antioxidants that can come into play with their own timescales. There are antioxidants that you introduce from the outside, and all this can contribute to the timescales, to altering the timescales on which free radicals created by radiation diffuse to the nearby tissue and cells, creating toxicity. And there is a little bit of a paradox in the way flash diagnostic is performed nowadays, because all the radiations is delivered within milliseconds, but then you wait weeks in order to assess the effect. Why? Because they mainly use structural imaging, meaning X-rays, CT, and this means that you wait for a biological effect at the macroscopic scales. This takes weeks to build up in order to have significant inflammation, redness as it comes, or whatever is going on. Something that you can observe at the centimeter scale is going to take time. So it's flash radiation, but it's a late assessment of effects. So what we would really need is a fast predictor whatever are the effects of radiation. And this has been really highlighted by a study by Konstantinos Koumenis and colleagues who showed that some of the applications where they showed very good healing in guinea pigs and cats showed late-term toxicity that occurred 9 months after the radiation was applied. So we really need something that can predict this type of effects before they happen, because otherwise it's the equivalent of shooting with your eyes folded, well blindfolded. So this is why at ELINP, when we proposed research on this type of systems, we had several pillars, and one of the pillars that was proposed was the early prediction of radiation effects using biomarkers in order to anticipate toxicity and to define very early the efficiency of radiation, both in cells and in animal models. This is a highly interdisciplinary topic, of course, because we have a time scale of radiation delivery, and this is physics. We have molecular effects, and this is chemistry, biochemistry, and then we have biological effects. We can look at it following the different phenomena that are ongoing. And, we try to detect the free radicals that are formed by radiation as they are formed. This would involve using EPR spectroscopy, for instance, combined with use of spin traps, and it would bear names such as radical detection or radical omics. I'm not particularly fond of omics names, but this is what it would look like. If we want to go a little bit further on the time scales, we would have to follow molecule transformations as they occur under the action of enzymes, and this was the equivalent to a type of enzymes titration, not looking necessarily directly at the enzymes, but at the transformation of their substrates, if possible in vivo. And if we want to look at further timescales, so after minutes towards hours, then we would have to follow up the buildup of the final concentrations of metabolites inside cells, and this is what we do by different methods such as magnetic resonance or mass spectrometry. And this is called metabolomics or radiomics in the context of radiation effect. And this is what we do. And we choose magnetic resonance in particular because it's non-invasive. We can look at a batch of cells or at an animal and apply radiation, and then wait for a while and apply another pulse of radiation and look again. So we don't have to necessarily interfere with the system. How is the radiation created? Well, the laser is impacting on a very thin target that can be plastic or thin metal target, such as a gold foil shown here. This is a recent review published in Frontiers in Physics that also cites our article that proposes the biomedical research at ELINP. So I like showing this slide. And upon impact on the target, it accelerates first the electromagnetic field from the laser, accelerates first the electrons from the target, and the electrons pull the protons after them, and this is radiation that can be used in order to impact biological targets outside of the interaction chamber. And the electrons can be further converted via Bremsstrahlung effects in a secondary target to photons of various energies. And the key here is the time within which this interaction occurs. So the initial laser impact on the target is tens of femtoseconds, as I told you, and then the time at which these particles are driven and arrive on the biological target can be on the order of nanoseconds. This is widely different compared to the timescales that are achievable in order to send protons or electrons or photons with conventional accelerators. So the flash effect is very, very pronounced with laser accelerated radiation. And there is one paper by Böge and Raschke and collaborators at a high-power laser site in Germany that investigated the effects of conventionally accelerated protons compared to laser accelerated protons on cells. And what they found was that with laser accelerated protons, the amount of free radicals produced was less, and the effects on free radicals on biological macromolecules such as proteins was less pronounced. They looked at a particular effect, is called nitrosylation of protein side chains. And this is what we want to look. We want to look at this type of effects. So in order to detect free radicals, of course, we can recur to magnetic resonance on the electron side. It's electron spin resonance if we want to look at the electrons. And then if we want to look downstream at all the molecules, we look at the molecules, and this is an induction. So we use an induction coil. I show here Mark Twain demonstrated one of the first induction coil. At his back there is Nikola Tesla. And how does this work in the context of biomarkers? Well, let's take a small molecule that is naturally occurring, so endogenous antioxidant. This is glutathione. And for each molecular site, if we take proton spectroscopy, we are going to observe a signal. And so we can recognize the molecular structure based on this signal. And if there is any change in the molecule related to an oxidative reaction, for instance, then we are going to observe this change. For instance, this molecule neutralizes the free radicals that can be created by radiation, and then when it does so, it transforms from its reduced to its oxidized form that involves connection between two GSH molecules, and the reactive oxygen species are quenched. And when doing so, you see a variation in the magnetic resonance signals at close to the interaction site. So this signal here labeled 5 is split into 2 signals. So you can recognize the kinetics of this reaction if you follow something like this. What we looked at was irradiated cells. So we actually took a bunch of glioblastoma cells, quite a lot of them, about 10 million of them. And we irradiated the cells with different doses and different dose rates. First, we aimed to follow the dose effect. So we used different doses on these glioblastoma cells that were grown in collaboration with the IFIN HH physics department. And we looked at all the molecules from these cells, and each molecule, if you look at the proton spectrum, can have one or several signals that make it recognizable, and the intensity of the signals is proportional to the concentration of a molecule. And we saw that if you irradiate at 10 gray, you observe changes in the spectra of metabolites from cells. Corresponding to the effects of radiation. Some of these molecules change concentration. So we went and we looked at the effect of several concentrations from these molecules as a function of a dose, and we used quite high doses because one of the hypotheses about the flash effect is that you need quite a high dose in order to have it occurring. We tested the cells are metabolically active even after this radiation effects. We looked at a couple of molecules. One of them is choline, which is known to be involved in the formation of cell membranes. And the other one is lactate, which corresponds to anaerobic respiration. You know that the tumor cells are not very well vascularized oftentimes, and they adapt to this type of hypoxic environment by preferring anaerobic respiration, which is not as efficient as aerobic transformation, as aerobic respiration, but can still be carried out in hypoxic media, and it produces a lot of lactate, just like our muscles do when we do training and we do not have enough oxygen. And what we saw was quite interesting. As we increase the radiation dose, the concentration of lactate increases. Here we take a ratio and we choose a metabolite whose concentration does not vary, just to normalize the concentration of the observable. And we did this in two contexts. We used radiation with cobalt-60 source at Erasmus Center in Tiffin, and we also irradiated in a clinical irradiator at Amethyst Otopeni. This is the second variation here, and in both cases we observe an increase in this marker that indicates increases in anaerobic respiration as cells are irradiated. And we see also decreases in the choline level, which indicates that some of the ingredients for the necessary membrane formation are probably oxidized by radiation effects. But more interestingly, we managed to change by a factor of 9 the dose rate. So we didn't change the dose, we changed the dose rate. And we see that the radiation effects on choline are reduced compared to the same effects, but at lower dose rates. So it's as if the dose rate does what we expect it to do. The free radicals produced interannihilate, because a lot of them are produced at the same time, and their effect on the membrane constituents appear to be less. This is a preliminary interpretation, but it goes in the direction where we expect it to do. And choline and lactate are not just any biomarkers, they are used in clinical studies. So in magnetic resonance spectroscopy in vivo, you can follow the choline to creatine ratio, which is what we followed here, and it's a very good predictor of tumor recurrence. So if this choline to creatine ratio does not go down, it's a pretty sure sign in magnetic resonance imaging that the tumor is likely to relapse within 5 years. So we've used clinically ascertained biomarkers in order to see the dose rate effects here. This is what setup we used at Amethyst radiotherapy, the dose profiling of glioblastoma cell tubes. The problem here is that we really have to use a lot of cells. So the quantity necessary is on the order of tens of millions of cells. So what we would like to do for sure is render this procedure more sensitive. But this is very difficult because the signal is proportional to the number of cells, and magnetic resonance is not a very sensitive technique. It has very good resolution in terms of metabolites, but it's not very sensitive. You need a high sample quantity. So we would like to use a new technique that has been invented in the last 20 years that proposes to improve a signal to noise in magnetic resonance. And the idea is you borrow some signal from free radicals, from electrons. And the idea is that you prepare the metabolites that you're interested in, let's say choline, let's say lactate, mixed with or pyruvate or whatever you have, glucose, mixed with free radicals. You irradiated the frequency of the electron spins of the free radicals in a preparation device called dynamic nuclear polarizing spectrometer. And then you transfer the sample to the patient or to the animal or to the test tube, and you observe the transformations of a molecule at this site. Doing in this manner, you actually achieve with a high sensitivity enzyme kinetics in vivo. And you can do this because by doing this preparation procedure, you can achieve factors of 10,000 sensitivity improvement for the NMR signal. So I'll show you a little bit of the results. This comparison between this new sensitivity enhancement for magnetic resonance for an implanted tumor, this DOGPO actually, and you can see the pyruvate to lactate transformation, which is part of the anaerobic transformation of glucose, and which is enhanced when there is a tumor present. And you can see the lactate concentration increasing here in bright yellow, which detects very well the limits of a tumor. And this is compared with just structural detection by magnetic resonance imaging, where you just detect water, so not the molecules, you don't have so much sensitivity. And it's also compared with PET-CT, which is the current standard in molecular imaging. So it's, you see it works very well. And it has very, very bright prospects. So this is another implanted tumor in a mouse. And you see the biomarker, pyruvate to lactate transformation in the tumor and in the normal tissue. And you can see that just a few hours after radiation delivery, you can see this biomarker going down. So you can prognose that the tumor is going to be healed. You don't have to wait weeks, you don't have to wait months. After a few hours, you can just look at this biomarker and say, well, here the radiation did its job or it did not do its job. And this is very, very interesting. This is another example in a rat model in the collaborating Cambridge group of Kevin Brindle and Arnaud Coman, where you see the reaction to radiation effects. So as soon as you deliver radiation, you see that the area where you detected the tumor is reduced via biomarker. And this is very, very important because oftentimes tumors do not shrink in size after a few hours of radiation application. They just change their metabolic activity. You don't know after a few hours whether it's going to shrink or not. But if you look at the metabolism, you can tell already that it's going to be all right. And this is very important for head tumor, for brain tumors, because there we do not have any alternative. PET-CT is not very good at predicting survival for the head tumor. So, and in any case, you can do this with magnetic resonance imaging. You can do a variety of biomarkers. So you're not limited to glucose that is labeled with fluorine 18. You can do antioxidants, as I'm going to show. You can do markers of aerobic respiration. You can do markers of lipid oxidation and so on. So we look at these transformations in vivo, and we try to have to enhance the time scale on which we can detect these biomarkers, because it takes a while. You inject whatever you inject. If you want to follow pyruvate, you inject it intravenously, and they do this in vivo in many hospitals already in San Francisco and They do this in Cambridge and they do this in Paris. You inject intravenously, and then you wait for the marker to arrive at the detection site, where they have done prostate, they have done lungs, they have done variety of tumors in humans clinically, and this can take 3 to 4 minutes. So you want to be able to follow the signal of a molecule of interest for these 3 to 4 minutes, and this is where the symmetry of magnetic transition comes into play, because, for instance, in a very symmetric molecule such as hydrogen, the nuclear spins, just like the electron spins in phosphorescence, are arranged in singlet and triplet states. And the result, a transition takes a long time to occur from singlet hydrogen, which is called as parahydrogen, to orthohydrogen. And you'd have time to follow such a transition. But in everyday molecules, you don't have such high degrees of symmetry. You have protons with magnetic environments that are slightly different from one proton to another. And therefore, the observation lifetimes are very short. So how do we do to enhance the observation lifetimes? Well, we do a little bit like the teenagers do when they are wary that they might have an asymmetry at the level of the eyes or at the level of the ears. Or they enhance one facial feature, they pout, or they put a tall hat or something like this. So this is what we do in the case of very general molecules. We apply a very intense radio frequency field, magnetic field from outside, B1, that masks the differences in symmetry for the molecules we observe. And doing this, we managed to observe quite long lifetimes in various types of molecules. This is a sugar molecule, and we did the same in a dipeptide. This is glycine-alanine, where the protons are asymmetric, and we reach lifetimes of 40 seconds. 40 seconds is the time constant of the exponential decay. So really, for the lifetime, you can have up to 5 times that. So you have quite a few minutes in which you can follow the molecule. And one nice application we did, even with these peptides, we followed it not in cells, but we followed it upon its interaction with liposomes. And since we enhanced the signal for magnetic resonance with dynamic nuclear polarization, the acquisition of a 2-dimensional spectrum like this took less than 1 minute. Generally, in order to acquire spectra, whoever did it in magnetic resonance, 2 dimensions takes hours or days. This was acquired in just 1 minute. In just 1 minute, we are able to see the interaction of a peptide with a liposome, and this was appreciated, and we are able to preserve the signal. And more recently, we demonstrated that we can preserve in the same manner the signal of endogenous antioxidants in the cells. And we chose this GSH molecule, glutathione. Glutathione is a tripeptide, so it has 3 amino acids, and we managed to preserve the signal at the level of 2 of these amino acids. One is the cysteine, that is actually interacting when the reduction takes place, and the other is the glycine at one of the termini of these peptides, and we get quite respectable relaxation decay times of 40 seconds or 6 seconds, and this is enough to follow the effects of a very fast oxidation reaction, such as the one that can be induced by radiation in real time, and it has been quite. It has been appreciated as such. Do I still have another couple of minutes? So this was in order to show what we can do with molecules lifetimes of magnetization. So this is a signal. We convince the molecule to adopt singlet triplet transitions like in phosphorescent, and then we can follow the signal for a long time. These are populations of singlets and triplets. Another idea that we put forward quite a few years ago, we patented and we published it in PRL, was to follow the coherent superpositions between singlet and triplet states in such quite general molecules. And these coherent superpositions, they induce signals in detection systems. And we interested that these signals that they induce are also long-lived compared to standard coherencies. And what this means is that if you Fourier transform them in order to get a signal, the signal is narrower. Of course, if you transform the time domain of a long-lived transition, then the signal is narrow and more intense. So you can get more intense and narrow signals from peptides or from amino acids or from quite general molecules. And what we have done really a month and a half ago, so really recently, when we went to the University of Florence, where there is a high-scale magnetic resonance facility. This is where I did my PhD. And we looked at the signals from these singlet triplet transitions in a proteins. This was for the first time at the world level. We detected such transitions before. They were detected in small molecules. We detected them for the first time in a protein. And not only did we detect them, but we were able to transfer signal from such coherencies that were excited here on a glycine in the protein to neighboring amino acids, meaning that we can get structural information because the amount of magnetization that is transferred from here to here or from here to here is proportional to the distance between the sites. And we observed something very interesting. As these coherencies are long-lived, the transfer of magnetization from one site to another is much more intense than in the classical case, meaning that you can map distances in a protein quite a bit further, and you can also get more reliable distance information. So these are comparisons between classical rotating frame over Hauser effects, they are called, so transfers of magnetization between one site and another, and long-lived coherencies-based transfers. And it's very interesting that in many cases we get more intense transfers, so this might be quite important for structural studies, and not only for structural studies. We saw something like this for a protein interacting with a biological partner, so it's also for interaction studies. So it may have quite some applications in also for the pharma industry. So I try to show a little bit what we do in order to have observables on various timescales for phenomena that can be of interest, mainly the effects of radiation applied on very short timescales, flash type radiation, and the markers that we can use in order to follow these effects. And these are a few publications from our group in the last time. We are trying to give some impact to our methods as far as we can. Many thanks to the members, all the members of the group, especially the PhD students. Ioana Fidel did quite a bit of work on these systems, and there are quite a few students who are starting now. Andrei Ciumeica just started, but he's quite enthusiastic. And many thanks to the undergrad students. We have undergrad students from the Faculty of Physics, maybe, who are quite enthusiastic. We are doing quite hard work. Diana Serafin, mainly, and I have to thank the various entities that financed our research and gave us measurement time. And with this, thank you very much for your attention.
Thank you very much, Professor Vassos. I have to say to my colleagues that I've been to your laboratory, I think a month ago. You do very impressive work, and the results presented today are proof of that quality work. And why not the possibilities to apply them in real life, as we all want to make a change in the real world. So if we have any questions from the room.
Hello, thank you for your presentation, very interesting. I wanted to ask, what's the importance of surface of irradiation when you're doing your experiments? Do you do like a localized irradiation, or can you control this parameter?
Being using something like 1/2 liter flasks, and that's an important question, as we are trying to get high dose rate. Usually this the tandem or the laser generated beams have a diameter of a couple of centimeters, something like this. So the irradiated surface is very small. And as we do not have a lot of sensitivity, we do not have still a dynamic nuclear polarization system. We cannot irradiate all our cells in one shot. So maybe we will be forced to do what they call in radiation oncology dose painting, so to move a sample within the dose. But this is going to introduce another variable, as not all the cells are going to be irradiated at all the time. So far we did not do, but we might have to do it.
Okay. Thank you.
We speaking of this,